Hello everyone, welcome back to Advent to Code. It's 2020, day 8. Let's get started. Day 8, handheld halting. Your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, which is your puzzle input. You should be able to fix it, but first you need to be able to run the code in isolation. Oh man, another one of these, huh? I've kind of implemented enough assembly languages in my life, I feel like. Okay, so we have something that increases the accumulator jump relative to itself. Okay. You're supposed to run until it would execute a single operation a second time. This is fairly simple. I'm like, if we get any more complicated on assembly stuff, on like implementing languages, I'm just like not gonna do it this year. But okay, we can do it today, I guess. I had enough of this last year. It was a lot of fun in like 2015 to implement a simple like language. But okay. So ACK increases or decreases a single global value. And the question is, what value is in the accumulator when that happens? All right. To get like random access to the instruction sequence, like I assume the input's going to be small enough that we could just use a list and look up in like a bad, do like a linear lookup, which sucks. I think we'll just use data.sequence though, which is like a random access data structure. It's not as efficient as, say, vector because it supports all kinds of wild operations like logarithmic time concatenation and stuff, I think. Yeah, that sounds right. But honestly, like the story with vectors and mutable arrays in Haskell is so confusing that I never use them. Just like understanding the documentation for them is just impossible. I could go look at a previous year where I actually successfully used arrays and like try to figure it out, but okay, so fine. Let's 2020, no, Advent of Code 2020. And we need new day. Oh, I'm like in a really old TMUX session, I think. Like from last year, maybe. Day 8. There we go. So we have containers, which means we have data sequence, and we're going to want a set, which is like the visited set, right? There you go, set and seek. Who could get them confused, right? And we're gonna have an exciting time here. I think our input is going to be a seek.sequence. Actually, is it called seek.seek maybe? Of, let's say, int? Yeah, it is called a seek, okay. But in this case it won't be an int, it'll be a data instruction or something. And an instruction is, well, let's read them in the order they were given in the spec. ACK of, I mean, I guess all these are in, so I could make them an argument and have a special type for argument. Maybe I'll need it in a future day, but not yet. And, I mean, if we really wanted to be specialized to just today's problem, we could, yeah, let's just factor this out. Data code equals ACK or jump or NOP. And, okay, cool. So we're going to want also text regex applicative to do our parsing. Map parse.lines, I assume, where parse equals match on instruction, I guess. And this should be super easy. Instruction is I guess I just want it's a code applied to an int. An int is I guess it's, let's see, it's identity over sim of plus, or else negate over a sim of minus. So we're parsing a function here. Sorry, that's not int. We'll say, well, that's a sign. Int is a sign over read many is digit. Import data char is digit. And we don't have code yet, that's fine. Code is, oh, we want to reverse parse as well. And we'll just return maybe an input, I guess. I don't know. Code is one of three possibilities. It's either ACK over sim, not sim, string ACK, or else it's, I mean, I guess instead of repeating these, I could use a sum of a list of things, but that's not really any better. Or else it's jump over a string jump, or else it's nop over a string nop. We need one more thing here, which is we didn't really have the space, right? psim of is digit, thank you, yes. I don't know, why am I using a maybe, right? Let's just, so we have a, let's do this again, like we have in all the other days. Import data maybe from maybe. So why is it mad about code here? So code should be a parser for function. Oh, I forgot. We actually split these out. So it's okay. It's actually instruction like this. Yeah. And now why are we mad here? An empty sequence, not an empty list. Oh, actually, I guess we need a bit more, which is that we need next to say convert a list to a sequence. Oh, it's not a list of sequence of instructions, it's a single sequence of instructions. All right, so that seems fine. And if we were to day 08, AOC input of 8, looks fine. And if we then said, do the stuff in main, right? Read file of input.text, prepare. Oh, we don't want to we just need to fmap it, right? Yeah, so it parsed a bunch of things. Cool. And we have a sequence of the results. Great. Not bad for 10 minutes work. We have it in a nice, friendly data structure now. Now, what exactly do we do? We kind of need to have a state for our computer, and we're going to like just kind of iterate that until we visit a state that it's ever been to. So we have like data state. I assume we won't need like the actual state monad here, so I'll just define my own state here that means something totally different and not worry about the name conflict. So our state is first and ac and pc, which are ints, and furthermore a set of int, which is where we have been. Okay, so if you, all right, let's go look at the spec real quick. When you jump, like jump, does it include an offset from the jump instruction? Jump +1 goes to the next one. All right. Okay, so we have a function called step, which is a function from state to state, basically, right? Step of state ac pc, let's call them A, P, and V, so Google doesn't, or HLint doesn't get mad at me for shadowing. It's making my code worse, by the way. I don't agree with the like no shadowing rules. I think they're fairly useful for records. And not that bad for like global functions usually. So next we're going to look up we'll go ahead and step even if we've already visited a thing, and then our iteration will be what's in charge of finding repeats. So we're going to say case It needs an input. Okay, so it needs a program as well to know how to run. Case, I assume there's a function in named this, right? If I mouse over it, will you tell me? Or not mouse, but hover. Doesn't look like it. Okay, data sequence does not export that. So, all right, Haskell data sequence. How do I use these things? Finite sequences, indexing. There's lookup, which gives you a maybe. And this is an infix version of that. Index, which cheats, which is what I was looking for. Interesting. These are. What's the deal with the difference in laziness between these things? Look up an element without forcing it. To insert the fifth element of the sequence X in a map M at key K. So when you look it up, it doesn't get forced. The argument? I mean, I understand what they're saying, I think. One of them... To retrieve an element immediately without forcing it. Ah, I see. The point is that this returns an A, and so to give you that A, it has to actually, like, return that A unwrapped to you, and, like, if you were looking at the index, you're necessarily also looking at the A. So you can't find out, like, whether there was a thing there or not without asking what that thing was. Whereas here, you can get a just wrapped around lazily. If the thing that you put into the sequence to begin with was itself lazy, then looking it up with lookup won't force it, because it can just give you a just of a thunk. And then if you actually care, you can look at the thunk. Okay. Now I understand why, but I'm just going to use index. I mean, I guess it's always an instruction, right? So actually we could say let inster code arg equal this. In case... Actually, you know what I could have done is... Again, I can just say case code of where, like so. Nop, we'll just say it's a state of we leave the ACK alone, increase the PC, and leave visited alone, I guess? We'll have the other thing's job be to track visitedness? Seems kind of silly, doesn't it? I think it's so. I think it seems silly. Let's update it here. Set dot insert VP. Well, let's actually say visit of p here, and we'll pull that out as a little function. Visit of x equals this. What are you upset about here? P is an int, and for some reason it expects a set of ints. All right, I have something else wrong, I guess. What's wrong with visit? I guess I just need to give like a type here. Visit is a function from int to set of int is. Okay, so this was all correct. Do I have the arguments to insert wrong? Oh, it takes a key and then the set. Yeah, I mean, I guess that makes sense. Okay. Whatever. I don't need this. The reason I factored it out is because we're going to use the same thing for ACK, right? ACK is a state of A plus. Where's our argument? Arg, there it is. Oh, actually, we don't even need to make this a function. They'll all share the same. We'll just call this visit prime then. Because we're saying where we have been, which we're always just adding p to. And lastly, jump is a little more exciting. It's state of leave the a alone, p plus arg, and we're not adding 1 to it. Yeah, okay. There you go. And yeah, you're right. We don't need these anymore. So is there like there's not a good way to say like run this function until, like you can say drop while and take while and so on. But the problem is I guess it is easy to tell whether we're in a visited state already. Okay. So what we'll say is complete is a function that takes a program and a state and returns the final state. Complete of P and S equals head of drop while. You know, I don't even need this S. Head of drop while not done. Iterate step P, where done of state P v equals set.member PV. Oh, you don't like this because, yeah, that's fine. And so part 1 then is ACK of complete I think that's it. Doesn't type check. We need an initial state. Well, let's just... And we'll define initial state here. The state of, I assume, 0, 0 set empty, right? It makes the most sense. That's where we would start. Sorry, let's look here. For its one instruction, the accumulator starts at 0. Okay, that makes sense. Okay, and they don't talk about program counters because that's not... Okay, it just starts at the beginning, sure. Yeah, this makes sense. And so we're looking for right before it does something the second time, is that right? Yes, cool. So does part 1 compile now? Yeah. Back run? That's a number. I'll take it. That's the right answer. Okay, cool. Day 8, part 1. That wasn't so bad, right? After some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a NOP or a NOP is supposed to be a jump. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or NOP, you can repair the boot code and make it terminate correctly. For example, consider the same program from above. If you change the first instruction from NOP plus 0 to jump plus 0, it would loop here, never finishing, okay? If you change almost any of the jump instructions, the program will still eventually find another jump. But if you change the second to last instruction from jump to NOP, then it terminates, sure. So fix the program so that it terminates normally. Okay. There's a few things we could do here. I mean, the obvious algorithm is just like try all the changes, but like the details of how we write that is what I'm thinking about now. And the main thing I want to do first is enrich complete to return more information about how it terminated. We could, use basically like an exit code here. Let's say a tuple of stop reason. I don't know. Sadly, that makes this we can just yeah, this is fine. Okay, so we need data stop reason equals infinite loop or normal. Now there is another possibility, which is that we could jump outside the last instruction. And it doesn't discuss that possibility. I'm inclined to believe that Eric wouldn't do that to us without warning us, but that's not exactly a guarantee. Yeah, I don't know. For now, let's just assume that never happens, and then if it does, we'll... Well, I mean, it's pretty easy to handle both, right? Finish or seg fault, right? We get a segmentation fault if you try to execute code outside of your program area. So now we just have to say, let final state be this. You know, we can, once again, we can just put this into the final state. Case final state of... Well, is that what I want? No. I actually... Oh, I can use a pattern guard here, right? If are done... Well, whatever. We need to amend done. And then further inspect... Okay, maybe I need to be a little bit more exciting here. Data mode is either running or a stop reason. I'm gonna have done return a mode, I think. Ugh. I really want to iterate. I want the mode to be part of what I'm iterating with, so it's what I get back as a result. So we'll just say iterate go here. And we'll say take while, or drop while running. Running, the first element says you're running, say. Running of, running equal. I could use like, I could derive eq for this stuff, but I don't really need anything more than just whether it's running or not. Running of anything else equals false. And now we just need this go, right? Iterate go of running and state is going to be our initial thing, and go of it's kind of something feels wrong about this, because go shouldn't really take a state as an input. It's invalid for it to ever be past anything but running state, right? I could do it and just ignore the state, but that's like wrong. This is an unfold, right? What's the type of unfold? It's in, I don't want any of these. Give me like a normal person's unfold, please. Hello? There's just a million implementations of unfold, and none of them are what I really want. Data list non-empty. Really? Oh, unfold R is what you're supposed to use? I see. So what does this give me? You give it a function that takes a state and returns a state and a value. Maybe one of those. And an initial state, and it gives you back a list of all the values that it saw. That's not really what I want, because I want to know the intermediate values as well. I just want a nice way to be able to stop. So maybe it's not strictly unfold R, but it's like the anamorphism of something else related to maybe tuples or lists or something. I'm not going to dig into like the documentation for recursion schemes at this time, but I feel like one of them should apply here. So I don't actually want I mean, I guess unfold R is fine. My B will be the program state, and my A will be a tuple of, well, actually, wait. Do I? Oh, maybe I'm dumb. Maybe unfold R is perfect. If my A is just the mode that we're in, no, because then there's no way to friggin' stop. No way to feed back into the program the fact that it should stop. I guess it doesn't matter if the program keeps going. But in that case, why not just write iterate? On a tuple. Something doesn't feel right here. I'm missing like the right abstraction for this. I have this operation which returns which can produce either a stop reason or a next state, right? You could capture that as producing a tuple of mode and next state, but then you could get like invalid stuff like, oh, I gave up and here's my next state, which makes little sense, right? But I guess if we always just return to the current state and not the next state, which is fine, we give it mode running, it just like feels wrong because it shouldn't take the mode as its input. It should be a function from state to pair of mode and state. And then the mechanism for iterating that should throw away the mode part. Ah. So maybe the point is the function that I'm iterating composes, like, get the first element of a tuple, as I was originally thinking, but composes it before calling the state transition function, not after, which is what you usually do. If you need more internal state while iterating, and you want to throw some of it away to get to the final result here, we need less internal state while iterating, but we want to carry around some extra result. I think that's the right idea. Okay. So did I mess up my types for the fact that I'm doing that? I don't think so. Well, it was also crystal clear when I didn't have to look at any code. Does it still make sense in my head? We're iterating. What is our thing? We pass our thing a state, right? What does it return? It like, what's really annoying is that it would be just so easy to hack something together here that it wouldn't even be like that hacky. You would just say like iterate like while there's something more to do, and then we would have another thing that looks at the finished state and says, oh, is there something left to do? Maybe that's... Maybe that is what I should... I mean, not exactly do something hacky, but the iteration doesn't need to know when to stop. We'll just never call it in an invalid state. I guess the whole problem is that I was thinking of this whole thing as being take while or drop while, I guess. But okay, I think what we can do is our go function, this is all silly. All right, so what we're gonna do is we're just gonna use step like we were before. Iterate step of state. But we're not gonna do this head drop while running thing yet. What we're going to do is we're going to map a function over each of these. And the function is to like decorate we'll call it we want to take the state and create a tuple of the state and like whether we think it's finished. What do you call that exactly? Inspect? It's pretty vague and non-meaningful. Oh, there's got to be a good word for this. Label, I guess, is like a little bit less bad. So something like this. I just need to write this. Oh, not step, right? Or is it called step? It is, okay. We need this label function. Label of s equals, well, probably case. We're gonna have to destructure our state, state of APV, where set member PV equals stop reason of infinite loop. Yes, correct. Otherwise, if p equals seek dot, I don't know how do you get the length of a sequence. Obviously, you could just call length, but that's like very slow. Size, maybe. Okay, it's a function named length, but it's in data sequence. Okay. In that case, it will be stop reason of completed, finished. Let's extract this out to a variable here. Size equals this. P less than 0 or p greater than size equals stop reason segfault. Otherwise equal running. But now label's returning the wrong type. We wanted it to return a tuple, right? So I guess we need just one more function, which is add label. S is label SS, like that. I'm sure there's a better like abstraction for like doing this, but I think I actually just want this to be okay. 1,000,000 type errors. That's exciting news. Oh, I didn't. There you go. To fix those now. What's wrong with all this? I forgot to compose something with step. Right, so iterate step. We wanted to say step.second is what we're iterating. And we don't want to start with state, we want to start with running state, like so. Like everything is wrong about this type for some reason. Which makes sense. I mean, I wrote kind of a big pile of stuff all at once and I didn't give any of it type annotations. Of course some of it's wrong. Oh, I don't want to add... Oh, this is right. I'm not actually... I don't want... Right, I wanted the program to just keep running brain deadly and I'll just never call it if it shouldn't be called. So we don't want this whole step composed with, and we just want state here. And we're just going to iterate step. So this actually was what I meant to do, but it's wrong. Okay, first of all, we don't want to return second of it. We're returning both the stop reason and the... Oh, I claimed I'm returning a stop reason, but I'm not. I'm returning a mode. Okay. You should give me like a probable cause here or something, right? No? So, state, you thought would be a function from state to state for some reason. So add labels a function from state to mode and state. Like that you already thought that, right? Yeah, that's not surprising to you. So this is all fine. In fairness, I could actually like I could beta reduce, or is this eta reduce? I don't even know. This doesn't help. Weirdly, it makes things worse. No, it just moves the original error that we had. So it's like expecting one more. Oh, I forgot to pass it a program. There you go. Okay. Now part 1 is broken, which is fine. We just want to only look at the second part of the result, right? Oh, you just, sure, fine. So now if we run part 1 again, it should give us the same result, 1939. It does. Okay. Now we can run a program and find out why it stopped. And then we can use just create a list of all the possible corrected programs. And then run each of them and see which one stops for the reason that it was finished normally. And so it's relatively straightforward to write all fixes. I could write something a little bit more general here, which I've written before but won't today, I think. All fixes takes a program and... God, it's almost easier to write it generically, isn't it? Not really. It returns a list of program, which is all the ways you could fix it. All fixes of this. If they're... Wait, is that right? Yeah. If we get to the end of the program and haven't applied any fixes yet, then there is no valid way to fix the program. Otherwise, all fixes of... code. What did I call these? No, instruction. Yeah, inster code arg equals case code of okay, so actually I need a little bit more we'll put the rest of the program here, and I want to label this as I so I can reuse it later. So if we had an if it started with an ACK, then it should be inster code oops, inster, no, wait, the acts stay the same. It's the nops and the jumps that we swap. Insert jump arg prog. So that's one option. And the other option is to just go. Let's put where go equals icons to all fixes prog. I'm lifting this out because we're going to use it twice. Jump inster nop arg prog go ac go. Is this wrong? Ah, yes it is. Okay, this is still wrong, but it makes more sense to me. Oh, you can't cons because we have a sequence, not a list. Ugh. All right. So I have to learn how to use the view patterns in dataseek, I think. So we can take a left view. But that's just a readable seek, right? I really should have just, I don't know, used a programming language where indexed access is easy. Haha. Okay, you know what? At the moment, we don't need any of the fancy stuff from sequence, right? So in fact, instead of taking a program, well, I don't know. We should, right? All fixes equals map seek dot from list of fix map seek dot to list where hello? Oh, there we go. And we'll just rename this to fix. And that needs to be indented a bit. There you go. Slightly wrong here. Why are you upset about seek.toList? Oh, it doesn't implement toList, it's just the one from foldable. I guess. Import data foldable to list. Yeah. All right. So that makes sense. Let's quickly try this out in the REPL. What are all fixes for seek from list of inster nop1 inster ac2 inster jump 3. So it says, well, you could try changing the first nop to a jump but leaving the ac and the jump alone. Or you could try leaving the nop and the ac alone but turning the jump into a nop. Yes, that looks correct. Great. You could quibble with the way I've named some of these functions. For sure. Fix and go are pretty shitty names, but I couldn't think of anything smarter, and they're private to all fixes, so it doesn't really matter that much. They're names with a very small scope. Now, we just want to write part 2 using all fixes and complete. What are we being asked to compute? What is the value of the accumulator after the program changes after you make that jump? Make that change. Got it. So actually, yeah. So we want like, well, you turn it int, obviously. So we want the accumulator of the second element of the first. Well, actually, let's return a list of ints. See if there's more than one way to do it, right? Then I don't have to use head. Succeed no, we're looking at first. Map complete prog, I guess. Okay, so I actually do need the prog here. Or, well, no, I don't, because I'm not actively using the original prog ever. What I need is map this, actually. Am I crazy? Is this correct? It can't be. So we compute all the ways to fix the program, giving us a list of programs. Then for each one, we run it to completion, starting with the initial state. And then we filter only for those states which completed successfully. And then for each such state, we look at what is currently in the accumulator. That actually looks right. So let's say succeed is a function from mode to bool. Will it type check if I do that? Oh, where? It does. Okay. Succeed of stop reason finished. True. Come back. Succeed of anything else is false. All right. Let's run it. There was only one program that met our conditions, and the result was 2212. That's the right answer. All right. Well, I mean, we had some teething problems here, so to speak, a few things that were difficult, but in the end, each time that the program actually type checked, it was correct, which was kind of nice. And many intermediate steps along the way. Also, we had a function that sort of just worked. Like, we tested all fixes, and it was right the first time. And we also tested our parser, and it was right on the first try. So like that's pretty successful, I would say. Anyway, let's get it committed. Just make sure I didn't like sneak in any changes I didn't really want. Ah, I knew there was something left over from yesterday. I realized I didn't need 4, so I didn't. I was going to make another commit that fixes that. I see. I made a few changes to yesterday to like make HLint happier, but I forgot to commit them apparently. Okay, well we can talk about those in a minute. In the meantime, let's just work on the current directory. Yeah, we wanted to list, and we needed a stop reason and a mode. And here was the exciting one. We had a fancier model of completion, and we implemented all fixes. Day 8, part 2. All right, so what the heck was I doing yesterday? I basically I think I just cleaned up HLint errors. Like it told me I don't need parens here. And it was upset that I was shadowing C. And then HLint didn't mind, but I thought it would be kind of nice to, instead of binding and then doing a case on the name, like present was not really a meaningful name, so I just replaced it with a lambda case here at the top level, which is kind of nice. Anyway, we'll stage all this. Yes. And here I renamed something because empty was shadowing something else. I called them leaf and node, which is kind of better than empty and full anyway, arguably. Day 7, HLint cleanups. Okay. Let's stitch all that together before day 8. Yeah. Okay, that's all for today. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.